So we will start by talking about instantaneous rate of change, right? So instantaneous rate of change is the rate of change at a specific moment, not the average rate of change, but at a very specific moment. So the instantaneous rate of change, right? Remember we had defined it before as the limit as h approaches 0, f of a plus h minus f of a over h. We said that that was the derivative at a. So here's what we have now, right? Provided that the limit, of course, exists, okay? So that's the instantaneous rate of change. You could either do it using the definition, and that is equal to f prime of a. But now we know how to use shortcuts to find f prime of a, the instantaneous rate of change at a specific point. Okay, so let's talk about this first example, all right? Enlarging circles, right? Okay, so we're going to talk about a circle that is, just getting wider and bigger, okay? All right, so it says, find the rate of change. What's another word for rate of change? Slope or derivative. Okay, find the rate of change of the area A of a circle with respect to its radius r. Okay, so we need to find the derivative of something. We're finding the derivative of A, okay, and the variable is r. That's what that tells you. So before taking a derivative, we need to write down what it is that we're taking the derivative of. It happens to be the area of a circle. And we happen to know what the formula for the area of a circle is, right? So now, okay, so now what I want is a prime. A prime is the derivative of a. So if we want the derivative of this, we're going to use our power rule. So the 2 will come down. So I have 2 pi r, right, to the power of 1. And there you have it. So, okay, so let me rewrite it another way. So a prime with respect to r, a prime of r, right, we're going to use function notation. So we have a function here. The name of the function is a, and then the variable is r, is 2 pi r. So there you have it. Okay? Another way to write this is dA dr. What this tells you, so dA dr is 2 pi r. What this is the derivative of a with respect to r. Okay? Now, interesting thing here, area of a circle is pi r squared. What's 2 pi r? The circumference. So what happened when I took a derivative, right? The area formula converted to that of the circumference. So it's like I went down 1 dimension, right? That's what taking a derivative will do. Okay, so now that's a prime of r. Okay, so now it says to evaluate the rate of change of a at r equals 5 and r equals 10. So basically, okay, so when r is equal to 5, a prime of 5 is equal to 2 pi times 5. So a prime of 5 is equal to 10 pi. And then what if when r is equal to 10? So now we have a bigger circle, right? R is equal to 10. So a prime of 10 is equal to 2 pi times 10, 20 pi. Okay, so let's think about this for a minute. We have a circle that's gradually getting bigger. The rate at which it's getting bigger is 2 pi r, right? Now, this is a prime of 5. What does that represent? That's the rate that the circle is getting bigger when the radius is 5. So this is the rate at which circle is getting bigger when r equals 5. So when r equals 5, this circle is getting bigger at a rate of 10 pi. So the 10 pi, that's 10 times 3.14. So the rate at which it's getting bigger is like 31 point something. Okay. Once the radius is 10, what's the rate at which it's getting bigger? 62.8. It's 20 pi, right? So what does that tell you? As the circle is getting bigger, the rate at which it's expanding is increasing. So it's expanding at a faster and faster rate. Okay? All right, we'll come back to that later. Okay, so now suppose r is measured in inches and a is measured in square inches. What units would be appropriate for dA, dr? Okay, so let's see. We got dA, dr, huh? Well, okay, so the area is measured in inches, so the change in area is inches squared. And then this is inches. So the units are inches squared per inches. Now, do we cancel inches and just leave it as inches? No. It stays as square inches per inch. Okay? We don't cancel. All right. Because the units of the change of area can't be inches. Right? Okay. Let's talk about motion along a line. Okay, so suppose an object is moving along a coordinate line, say an s-axis. It doesn't always have to be x and y-axis, right? It could be d and y. It could be s and v, okay? So suppose this is the s-axis, and you've got an object that's moving along. So at t equals 0, it's here. At t equals 1, it's here, and so on and so forth. Okay? So suppose this object is moving, and we know its position S, okay? And the position is given to us as S of t. Okay? Now, so if S of t is the position, then what is the displacement? The displacement of the object over the time interval from t1 to t2 is, here it is. This is the formula for displacement. It's S of t2 minus S of t1. What is S? Position, right? S is your position. S of t2 is the final position. S of t1 is the initial position. That's displacement. So now, suppose at t equals 0, this thing was here. At t equals 1, this thing was here. And then at t equals 2, it's here. Right? What happened? It came all the way to the edge, and then it went back around to here. So now what's the displacement? It's the final position minus the initial position. Minus always means difference, right? So the difference in its final position with the initial position. So the displacement is just this. At the end of the day, how far away are you from where you started? It doesn't matter what you did in the beginning, in the middle, okay? Now, let's talk about average velocity. Average velocity, we know, okay, so we have to memorize this, right? Average velocity is total displacement over total time. So that, okay, so there is a typo here. It's S of t2 minus S of t1 over t2 minus t1. And guess what? You got to memorize this. Yeah. Okay, but you know this already, right? Average velocity is slope of the secant line. It's final minus initial. It's total displacement over total time. Final minus initial over the total time. Okay, that's average velocity. Then we've got instantaneous velocity. There you go. The instantaneous velocity is the derivative. So average velocity, it's the slope of the secant line. Instantaneous velocity is the slope of the tangent line. So that's the derivative at point A. Okay? So this too, you have to memorize. Okay? So V of t is S prime of t. Okay? Just take the derivative. That's it. Speed. Speed is the absolute value of velocity. Because if you're going 5 miles an hour, that's your speed. If you're going 5 miles an hour north, that's your velocity. So if your velocity is negative 5 miles an hour, how fast are you going? 5 miles an hour. That's your speed. That's your direction. Okay? So when you take the absolute value, that's your speed. Okay, those of you taking physics now, you're welcome. Acceleration. All right, how do we find acceleration? Acceleration is velocity over time. Change in velocity over change in time. How fast your velocity changes, rate of change of velocity. Okay, so this is rate of change of velocity. What's another word for rate of change? Or derivative. So it's the derivative of velocity. All right? So acceleration is v prime of t. But how did we get v of t? We took a derivative of s. So or it's s prime of t. So you have your position. You take a derivative, you find velocity. You take a derivative of that, you find acceleration. Yeah.
For the rate of change of velocity, is that the same thing as like delta v?
Yeah.
Okay.
Delta v over delta t is acceleration.
Okay, that's exactly what in physics today.
Yeah, rate of change is not delta v. Rate of change is delta v over delta t.
Oh, but like delta means rate.
Delta means change.
Change.
Delta means change, not rate.
Okay.
Delta over delta t, that would be rate. Okay. All right, so how do you know whether you're speeding up or slowing down? Right, so when velocity and acceleration have the same sign, you're speeding up. When velocity and acceleration have opposite signs, you're slowing down. Okay? All right. So let's recap all this S and V and A. Your position is S of t. Okay? Then V of t is S prime of t. A of t is V prime of t, which is S double prime of t. Okay? Time. Okay. A dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second, which is about 109 miles per hour. It reaches a height of this. So that's the position after t seconds, right? So height, position, these all mean the same thing. So this is the position. Okay, after t seconds. So that's the height of the rock. Boom. Position could be horizontal or vertical displacement. Okay, so if you see here, the rock shoots upward, and then obviously after a while it's going to come back down. So here we have how high does the rock go? All right, so take a look at what's happening here. The rock goes up. Okay. Now, when it initially starts, it's got an initial velocity of 160 feet per second. So here, it starts with 160 feet per second velocity. Now, I'll tell you, now here is this question. As the rock is going up, okay, as it's going higher and higher, Is it speeding up or slowing down?
Slowing down.
It's slowing down. So as it's going up, it's slower, 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 slower until what happens?
Stop.
Here, instantaneously, the velocity is 0. That's when it changes direction, and then it's allowed, and then it'll come back down. Okay? So, how high does the rock go? The rock goes as high as, until the velocity is 0. So we're going to find the time, first of all, when v of t is equal to 0. Okay? All right. So what do we have? We have s of t. Well, let's first find v of t. V of t is s of t prime, s prime of t. So now, what is the derivative of this? 160t, the derivative is 160 minus 32t. So that's v of t. And now we want that to be 0. Right? So t is equal to 5. So it takes 5 seconds for it to go up there. And then, in those 5 seconds, it's slowing down, slowing down, slowing down, slowing down. T equals 5 seconds. Velocity is 0, and then it just goes back down. Okay? So now, that's all fine and cool and lovely, but that's totally not what the question is asking. The question is asking, how high does it go? Well, any way for me to figure that out? Plug it into the position function. So now, s of 5 is equal to 160 times 5 minus 16 times 5 squared. Okay, if anybody were to tap you on the shoulder while you're solving one of these problems and ask you, what does that represent? What does that represent? Position at t equals 5. Fantastic. So s of 5 is equal to 400, which means it's 400 feet. Do we include units in these? Okay. Okay, next. What is the velocity and the speed of the rock when it is 256 feet above the ground, on the way up or on the way down? Okay, so it started here and then it goes up a total of 400 feet. On its way, here it's at 256 feet, right? And then it goes up 150 feet more. And then when it's going down, it's at 256 feet again. So let's see what's the velocity there and what's the velocity at that point. So how are we going to do that? We need to know the velocity and the speed. Okay, so what do you guys think here? So first what I want is, what is the velocity when it's at this point? What is the velocity when it got there? Well, how long did it take for it to get there? How do we know? Less than 5 seconds, definitely, but how do I know? We got to figure it out, okay? So, when was the rock? The question is, when was the rock at 256 feet? Okay? So basically, when was the position equal to 256? You see that? Isn't that wonderful? Yeah.
So because
You
would do that on the opposite side, put it in, so set that equal to
Set that equal to 256, right? When was the position equal to 256? And now, let us, okay, so what are we going to do? First of all, it looks to me that this is divisible by 16, this is divisible by 16. I bet that's divisible by 16, is it? That's, what's 16 squared these days? 256. So first, you know what? Let me just like simplify this for me. Right? So I get 10t minus t squared is equal to 16. Oh my God, that's like a quadratic equation or something. I know. So 0 is equal to t squared minus 10t plus 16. Can I factor this guy? T minus what? 8t minus 2. So t is equal to 2. T is equal to 8. How come I have two answers? One is on the way up and one is on the way down. Okay, do you see how the physics of, like, how the physical process of it just falls out of the math? It's magical. This is what drove me to major in physics. Right there. So, on the way up, huh? So, on the way up, we need to find the velocity at t equals 2. The velocity at t equals 2, that's 160 minus 32 times 2, right? I'm plugging it into the velocity function that I found before. So v of 2 is equal to 96 feet per second. Okay, on the way down, v of 8 is 160 minus 32 times 8. How much is that? Negative 96 feet per second. Look at how beautifully symmetric. On the way up, okay, so what's the velocity on the way up? 96. What's the velocity on the way down? Negative 96. What's the speed in both cases? Now, do you see how beautiful it is? It's got the same speed at the equal points, just opposite directions for velocity. Okay, Jackson. And now the speed is 96 feet per second. So it was going just as fast on the way up as on the way down, but one is on the way up, so it's positive, and then one is facing down, so it's negative. They would be, because it's a parabola. If you're looking at the velocity at the same height, then they have to be the same because it's a parabola, and the parabola is symmetric. Right. Okay. What is the acceleration at any time t during its flight? Okay. So after the plasma, what is the acceleration? Well, we know that v of t was 160 minus 32t. Okay. A of t is v prime of t. So that's negative 32. Okay. That means a of t, we need units now, is negative 32 feet per second per second. Okay? Right. It's feet per second, so then you can write it as second squared. I like per second, but that's fine. Okay. Same. Okay. When does the rock hit the ground? So when the rock hits the ground, its position is 0. Okay? Now, you could do it in a couple of different ways. First of all, remember what I said about it being symmetric. That means if it took 5 seconds for it to go up, it's going to take another 5 seconds for it to go down. So you know that it's going to take 10 seconds for the entire flight. Okay? So 2 times 5 is equal to 10. So this is, method 2. 10 seconds. Or we know that when it hits the ground, its position is 0. So that means 160t minus 16t squared is equal to 0. Right? And again, if you take out a t, it's 160 minus 16t is equal to 0. From here, I get that t equals 0. From here, I get that t is equal to 10. So again, it's on the ground twice. One at t equals 0, which is when the problem started, and then one at t equals 10, which is when it got back. Either. Okay? All right. So now, a particle moving along a line has a position at any time t is greater than or equal to 0 given by the function this. So that's the position. Where s is measured in meters and t is measured in seconds. Do you see what I did there? I didn't just passively read this. While I was reading, I underlined and I marked some important information. Okay? All right. So now, let's see what we need. This is what we have. Let's see what we need. We need the displacement. When, though? During the first 2 seconds. So, when t equals 1 to... Okay, displacement is the difference between where you were at the beginning and where you are now. So that's going to be displacement is going to be s of 2 minus s of 0. S of 2 is negative 1 minus 3, negative 4. So displacement is negative 4 meters. Most common mistake with these is students either forget that displacement is, s of 2 minus s of 1. And then there's always a negative mistake here. So just, do your bookkeeping properly. Okay, average velocity. This is total displacement over total time during the first 4 seconds. So average velocity is equal to s of 4 minus s of 0 over 4 minus 0. Where am I plugging these numbers? Into the original s, right? So s of 4 is 3 minus 3, 4 minus 0. So that's 0 meters per second. So the average velocity is 0. How can that be? Is it not moving? It's moving, yeah.
Well, it doesn't start out slowly to or no. It's because it's going in a negative direction.
Right, so it went, and then it went a certain distance, and then it must have turned back, right? Because it must have turned back because its initial and final positions are the same. So it went back and forth. So if it went forward at a velocity of 92, and then it came back at a velocity of 92, its average velocity was 0. Okay. Instantaneous velocity. So if average velocity is the slope of the secant line, instantaneous velocity is the derivative when t equals 4. So v of t is equal to s prime of t. So v of t is, the derivative of that is 2t minus 4. At t equals 4, I want v of 4, and that equals just 4. What are the units? Okay, let's pause here and look at form and notation, right? Do you see how everything is labeled properly? This is v of t. This is v of 4. What I don't want to see is, right, v of t is, I don't know, 2t minus 4, and then that's equal to 4. No, because one is v of t, one is t. Or, you shouldn't have like random equations on random parts of the page. Have a logical follow through with this stuff. Okay, the acceleration is v prime of t, which by the way is the same as s double prime of t. Okay? So a of t, what's the derivative of the velocity here? How much? Is it 0? 2. When t equals 4, what is it? 2. When t equals 7, what is it? 2. So a of 4 is 2 meters per second per second. How do you know which part? Well, this is the velocity. You take a derivative of this. So here, the exponent of t is 1. So when it comes down, it's 1 times 2, 2, t to the 0, which is just 2. And then the derivative of the negative 4 is just 0. So now the acceleration is 2, and that's a constant. So it means the acceleration is constantly 2. Okay, if you say it out loud, it sounds a little bit better. So look at this. The acceleration is velocity over time, meters per second per second. Do you see how it looks more like a rate over there? Meters per second per second. So it's not meters per second squared. There's no such thing as second squared. But, we just abbreviate that to meters per second squared. Okay. Describe the motion of the particle. At what values of t does the particle change directions? Now, when it says describe the motion of the particle, we're not looking for adjectives. It was pretty. It was nice. It was fun. That's not what we're looking for. We're looking for what is it that this thing did. Okay? So, yeah. It's when the velocity is 0. Okay? So, we look at when v of t is equal to 0. Okay? Because that's when the critical things happen. All right. V of t is 2t minus 4. So when is that 0? When t is equal to 2. Okay. Now, let's make a timeline. Okay, so this is going to be, okay. This wasn't happening until the beginning of time, right? It started very specifically when t was 0. So here, t is equal to 0. At t equals 2, what was the velocity? 0. So this axis represents v of t. Okay? Now, between t equals 0 and 2, was the velocity positive or negative? So how do you know? So what you do is you plug in a number here, like let's say t equals 1 into the velocity, and you get a negative number. After t equals 2, is it positive or negative? Positive. So look, here you have negative velocity. What does that mean? It's going in the negative direction or positive direction. So what we say is moving in negative direction from 0 to 2, moving in positive direction from 2 to infinity. Okay? And it turns around at t equals 2. Well, because, if it were keep going forever. Okay? All right. So this is more of what we've done before. Let's talk about some particle motion. Yeah. So a particle moves on the number line shown here in part A. So like it's on this number line and it can only move along this line. So either right or left. Part B shows the position, right, as a function of t. So this is 0, and then it's moving to the left and right of 0. Okay, so look, here's more physics for you. This is a position time graph. If you just look at a value, it can tell you where the particle is. At t equals 1, the vertical, right, it's at s equals 2, so it's at position 2. So that's one piece of information you could get from this. The slope tells you the what? The velocity. Okay, so the slope tells you the velocity. All right, so here in this first part, what is the slope? 2 over 1, right? Because it goes up 2 over 1, so the slope is 2. What is the slope here from 1 to 2? 0. What is the slope in this chunk here? Negative. Well, it goes down 4 and over 1, so negative 4. What about here? M equals 0. And here, M equals, it goes down 2, no, over 1, so M equals negative 2. Okay? Now, so here, the velocity is positive 2. What is it doing? It's going to the right. When the velocity is 0, what is it doing? It's at rest. Okay, so when is the particle moving to the left? Right. Specifically, it's moving to the left from 2 to 3 and from 5 to 6. When is it moving to the right? 0 to 2, and that's it. There's 0 to 2 or 0 to 1? 0 to 1. Hang on. We close the endpoint 0 to 1. And then when is it standing still? From 1 to 2 and 3 to 5. Okay. Yeah, it's so at the 6, 2, you could close it, and then at the 0, you could close it. Okay, so let's graph the velocity. So remember, the velocity was the slope, right?
Yeah.
Okay, so from 0 to 1, it's 2. We've done this before. From 1 to 2 is 0. From 2 to 3, what was it? Negative 4. And then from 3 to 5 was 0. And then 5 to 6 was negative 2. Okay. What about the speed? What is speed though? Oh, here, yeah, we close it here. What is speed? Absolute value of velocity. So here, velocity is 2. Its absolute value is 2. Here, velocity is 0. Absolute value is still 0. Okay, here, absolute value of negative 4 is 4. So from here, and then it's 0 from 3 to 5. And then the absolute value of the velocity here is positive 2. Okay. Huh? Graph paper. Yes. Okay, so this is the homework due tomorrow, right? And then we finish the chapter tomorrow. We